All right, it's gone.
All right, good. All right, today we have improper integrals. Okay, so improper integrals come in three forms. So the first one is when we have infinite limits of integration. Okay. So for example, we're going to look at these later, but I'm just going to show you the types. So we have -1 to infinity of dx over x squared, negative infinity to 0 of e to the x dx, and negative infinity to infinity of dx over 1 plus x squared. So both of these, all three of these have some sort of infinity in their limits. This one has 2 both at the bottom and the top, so we'll learn how to deal with that. The second type, so this is type 1, second type, is when we have an infinite discontinuity. Infinite discontinuity within the interval of integration. Okay, so an infinite discontinuity within the interval of integration means that there's going to be like an asymptote, right? So i.e. asymptote. Okay, so an example of this might be -2 to 2 of dx over x squared, because in the middle there we have where x is 0, this thing is undefined, right? Okay. Or +1 to 2 of dx over x minus 1. So here, the difference is that this is somewhere in the middle of our interval, the 0, but here we have 1, right? And so 1 is, there's an asymptote right at 1 here, so it's on the outer edge of our interval, right? And then the other one, another one might be from 0 to pi of tan x dx. That one has a, where's the asymptote there?
And pi, right?
Pi over 2.
Okay.
Yeah, for tangent is pi over 2. All right, so infinite limit of integration, infinite discontinuity, and the third type is both problems. Okay? So type 3 is we have both of the above. Okay, so for example, 0 to infinity of dx over root x. So this one here has a problem at 0, right? There's an asymptote there, because that's not defined, but it also has an infinity. So we got a problem there. Negative infinity to infinity of dx over x squared minus 9. That's got all sorts of problems, right?
Yeah.
It's got 2 infinite limits, and it's got,
2 asymptotes, right?
what's that?
Like 3 and -3.
3 and -3 would be asymptotes. It's really got 4 issues here, right?
Yeah.
Yeah, okay. Another one would be 1 to infinity of secant x dx. So secant x, it's got to have, ooh, there's lots of asymptotes there, right?
Yeah.
Yeah, okay. I don't know if we're going to actually do that one. Maybe I meant secant inverse. Think about that. Okay. All right, so I'm going to erase this now, and we're going to start going through some of these examples. we take 1/x², which is our f of x, and we look at just an interval from 1 to 2, 1/x² in the first quadrant looks something like that. And so from 1 to 2, we have just that little area there. Okay, we could find that area, right? That would be integral from 1 to 2 of dx over x². So if we integrate that, what do we end up with? What's the,
-1/3.
no, we're gonna go up a power. So right now it's at
Oh.
-2, so it's gonna go up to
-1/x.
-1/x evaluated from 1 to 2. So that gives me -1/2 minus a -1/1. So that's -1/2, so that turns out to be +1/2. And it better be positive because we have a positive area there, right?
Yeah.
Okay, so now we're gonna look at the same curve, but we're gonna look at what happens when we increase this. Instead of going to 2, we're gonna go to 3. So if I do from 1 to 3 now, look what happens. We have, I can just jump to the step here where we've already done the integral, right? I have -1/x evaluated from 1 to 3. So that would give me -1/3 plus 1, or 2/3, right? Okay. Now, if I do the same thing, and now we go from 1 to 4, okay, we're gonna get -1/x evaluated from 1 to 4. So that's gonna be -1/4 plus 1, or 3/4. So look what's happening to these values as we start increasing our area here. What happens to the values? We go from 1/2 to 2/3.
Oh, are they converging?
They're converging, right? They're getting closer and closer to what?
1.
1, right? So if I were to do, let's pick a larger number. Suppose we did this integral from 1 to 100 of 1/x² dx. That would be very far out. Okay, so that would be, let's see, -1/x from 1 to 100. Now, following the pattern, we can see that that's going to be -1/100 plus 1, or 99/100, right? Okay, so now this graph goes on forever and ever and ever, right? So we want to look at what happens now when we have the integral from 1 to infinity of 1/x² dx. Okay. So we can't really actually plug in infinity, so we have to turn this into a limit. Okay? So we're going to say the limit, and we're going to just choose another variable, say b. b goes to infinity of the integral of 1 to b of 1/x² dx. And so we know that that is going to be the limit as b goes to infinity of -1/x evaluated from 1 to b. And then what happens? We have, this is going to be the limit as b goes to infinity of -1/b plus 1, right? Okay, so now as b gets towards infinity, what happens right here to this first fraction?
It goes to 0.
Goes to 0, right? So this is equal to 1. So we say that this integral here converges to 1. Okay, so it's gonna get infinitely close to 1. Does it actually equal 1? No, but it's so close that we call it 1, right? Okay, so even though that curve, this curve right here, goes on forever and ever and ever, it actually has a finite area, right? We can actually calculate the area. Right? Now, we're going to look at another example of a very similar curve of 1 over x on 1 to infinity. So 1 over x has a similar picture, correct?
Yeah.
Right? And we're going from 1 to infinity. So what would the integral look like?
Limit as b goes to infinity of, from 1 to infinity.
So 1 to b now, because
Or
you've
b.
replaced that, right? Of 1 over x dx, right?
Yeah.
Okay. So now, what happens when we integrate 1 over x?
ln of absolute value of x.
Okay, good. So we get a limit as b goes to infinity of ln absolute value x, right? Evaluated from 1 to b. We can actually, can we drop the absolute value here?
Yeah.
Yeah, because b, we know b is positive because we're going to infinity. All right, so we have the limit as b goes to infinity of ln b minus ln 1. All right, ln 1 is
0.
0, and the ln, as b gets close to infinity, what happens to ln?
Those are just keep going.
Just keeps going, right? So does it converge to a number? No. So this is also infinity, right? Okay, so as we get close to infinity, this, what we say is that this integral diverges. In other words, there's no finite area there. Okay? Does that make sense?
Yeah.
Okay. All right. So let's look now at the integral from 1 to infinity of 1 over x cubed dx. So how would I rewrite that?
Like with that limit,
With a limit.
as b goes to infinity of 1 to b, dx over x cubed. And that's,
Okay.
So negative 1/3, or
No.
negative 1 over 4x, or 2x squared.
Okay, so we're gonna go up a power.
Yeah.
So we really are starting with x to the -3 power.
Yeah.
So we're gonna go up to x to the -2
Yeah, so,
and divide by -2. So -1/2,
yeah,
is that right?
yeah.
Okay, so I think sometimes it's helpful to write it this way to see that we're going up in power. So we have the limit as b goes to infinity of -1/2 x to the -2 evaluated from 1 to b. So we're gonna plug in b, so we have -1/2 b to the -2 minus a -1/2 times 1 to the -2. Okay, so,
That should go to 1/2, right?
it will, because this goes to what?
0.
0. That's 0, and this is a half, so this is 1/2. Okay. So, look at the exponent down here, that's a 3, right? And then the one that had a 1 here, this is like x to the first power, we found that diverged, right? Okay. So, we're gonna come up with a general case of this. Certainly, if I had y equals x squared, or the integral from 1 to infinity of x squared. Would that converge or diverge?
Diverge.
Diverge, certainly, that area is so infinite, right? Diverge. Okay, so, in general, we're gonna look at the integral of 1 to infinity of dx over x to the p power, okay? So, that's the same thing as the limit as b goes to infinity of integral from 1 to b of dx over x to the p power, okay? So, I'm gonna write this out. With a negative exponent, because I think it's easier to integrate that way. So the limit, as b goes to infinity, integral of 1 to b of x to the negative p dx, right? Okay, so p is just some constant. So if I integrate that, I want to go up a power, right? So I would get the limit as b goes to infinity, and I get x to the negative p plus 1, right?
Yeah.
And then I'd have to divide by that, negative p plus 1, is that right?
Yeah.
Okay, so the way that that's normally written as the limit as b goes to infinity of x to the 1 minus p over 1 minus p. It's cleaner that way. And we're evaluating that, sorry, from 1 to b. Okay, so that's, b is being plugged in for x, right? Okay. So we get the limit as b goes to infinity of b raised to the 1 minus p over 1 minus p minus, I'm going to plug in 1, so I have 1 over 1 minus p, right?
Yeah.
Okay, so let's see. Now, as b goes, so let's look at the different cases. Suppose that b is b is going to infinity, right?
Yeah.
So we need to know what's happening with this exponent. If for some reason this exponent takes this b and puts it down into the denominator, then it's going to go to 0, right? If it keeps it in the numerator, it's going to go to infinity, right? Okay. So what would put that down in the denominator?
If p is greater than 1.
Okay, so if 1 minus p is less than 0, or p is greater than 1, right? So if p is greater than 1, that's going to throw this down into the denominator, and we get, this part will become 0, right?
Yeah.
Okay, and so our limit, so if p is greater than 1, then this limit, as b goes to infinity, of b to the 1 minus p over 1 minus p minus 1 over 1 minus p is going to equal what? Sorry.
It's greater than 1. It'll be,
This part we said would go to 0, right?
yeah.
This part has nothing to do with that limit, right?
Yeah.
So it's just going to be negative 1 over 1 minus p. Okay, and to make it a little cleaner, we can say that this is 1 over p minus 1, right? Okay, so that will converge to 1 over, wait a second, why do I have 1 minus p? Did I forget a negative sign? Why am I missing a negative sign? Oh, I know why. You know why I'm I'm missing, and am I maybe, no, it's P. So I raised the power by one, right?
Yeah.
So I got negative P plus one, I'm dividing by negative P plus one, from one to B. Okay, so then I have x to the one minus P over one minus P, okay? So I have B to the one minus P over one minus B minus, oh, I know, wait, so this is one to the one minus P? Still should be one, shouldn't it?
Yeah. Yeah, I don't see what that would.
Minus one over one minus P. Okay. All right, I'm gonna have to look this up in a second. Oh, no, I have it right. Never mind. I'm sorry. This is correct.
Okay.
So this converges to one over P minus one.
Okay.
So if P is greater than one, this is gonna converge, right?
Yeah.
Okay. If P is less than or equal to one, we would have the limit as B goes to infinity of B to the one minus P over one minus P minus one over one minus P. Okay, so now, P is less than or equal to one, so that means that this is staying in the numerator, isn't it? This,
Yeah.
this part here
So it'll be
is,
infinity, right?
so this goes to infinity, right? So the B is gonna go to infinity, it doesn't really matter what this is, right?
Yeah.
Okay, so this means that this diverges. So we have one case where it converges and one case that it diverges. And this is important when we get to series. We need to know this for series. Okay. Let me look at another example now. Okay, so this is from 0 to infinity of parentheses 1 minus x e to the negative x dx. So here we have a combination of something we learned previously, right? We learned how to do, what do we need to use?
Oh, by parts?
By parts, okay. So we're gonna still take the limit as b goes to infinity, integral 0 to b. Now, we have 1 minus x e to the negative x dx. Okay, so in our Liate thing, what do we make our u here?
Would it be e to the x? Or,
So,
I forget, I'll look at it.
Liate. So log, inverse trig, algebraic, trig, and exponential. So exponential is the last one.
So 1 minus x.
So algebraic is 1 minus x. So u equals 1 minus x, so du is equal to negative dx, right? And then dv would be what?
E to the negative x dx.
E to the negative x dx, and v is negative e to the negative x. All right, so we have u times v, so we still have this limit as b goes to infinity of u times v, so 1 minus x times, I'll put a negative sign in front because it's e to the negative, it's negative e to the negative x, right? Okay. Minus the integral from 0 to b of b du. So that becomes, those two minus signs will cancel out, and I just have e to the negative x dx. let's see what happens. So this integral here, integral of e to the negative x is what?
Negative e to the negative x.
Yeah, it's negative e to the negative x. I've got another negative sign out front, so it's gonna cancel out.
Yeah.
So we're just gonna get e to the negative x. So I have minus 1 minus x, e to the negative x, okay? Evaluated from 0 to b. All right, so let's put b in. Everywhere we see an x now, we're gonna put a b in, right? So we have the limit as b goes to infinity, negative 1 minus b, e to the negative b, minus e to the minus b, minus parentheses. Now I'm gonna plug in 0, right? So negative 1 minus 0, e to the 0, minus e to the 0. Correct?
Yeah.
Okay, so let's see what happens. This b, since we're going to infinity, this is gonna drop down to the denominator, right? And what are these gonna go to?
Those are gonna go to 0, right?
0, right? Because they're gonna drop down to the denominator, and b is getting really, really large, so they go to 0. Okay, so now I have here, let's see, I have, this is 1, isn't it?
Yeah.
Minus 1, but in front I have a minus, right?
So it'll go to 2.
So it's minus a negative 1 minus 1, so it's gonna be a total of a positive 2, right? And you know what, I think I made a mistake here. Did I say that this should be plus 1, plus e to the x here?
Oh, yeah.
All right, so I made a mistake, sorry. So this is plus, right? So that means this is plus, that's plus, and so that's 0. Okay. Okay. Now let's look at what happens when we have two infinite limits, or two limits that are infinity, so negative infinity to positive infinity. So if we have integral from negative infinity to positive infinity of some f of x dx, then we have to split this into two integrals. So we're basically spanning the entire number line from negative infinity to infinity, right?
Yeah.
And we assume that because we are writing this as an integral, that we can actually integrate this function everywhere on that range or domain. So it doesn't make a difference where we split it. So you could just choose a number. You could say, okay, I'm going to make this negative infinity to c of f of x, dx, plus c to infinity of f of x, dx, right? Some constant. Now generally it's useful to put a number in for that constant, right?
Yeah.
And if it works, I would say use 0. So negative infinity to 0 of f of x dx plus 0 to infinity of f of x. Then we have to rewrite each one of these with a limit. So we need to choose different variables because we've used b, so we can use k maybe. So let's use the limit as b goes to negative infinity of the integral from b to 0